14.3, we're going to talk about partial derivatives of a function. Last time we talked about a function in 2 or 3 variables. Today we're going to talk about the derivatives, or how to take the derivatives or rate of change of a function in 2 variables. So in general, we define the partial derivatives of a function in the direction of x, in the direction of y, and you have 2 variables. F sub x, or the partial derivative of f with respect to x at point a, b, is equal to the limit, using the definition of the limit of the function, f of a plus h, comma b, minus the value of the function, f of a and b, divided by h, while h goes to 0. If this limit exists, then you say that you have a partial derivative of f with respect to x, or you have the derivative of x in the direction of the derivative of f in the direction of x, if the limit exists. With the same process, you can define a partial derivative of f with respect to y as the limit of f of a and b plus k minus the value of the function f of a and b divided by k, while k goes to 0. These are the official definitions of partial derivatives of a function, or rate of change of the function with respect to free or independent variables, f sub x, f sub y. Let us go over an example to see what's going on. In general, if you have a function in 2 variables, x and y, and z is equal to f of x and y, z is a function in 2 variables, f of x, f sub x, can be written as partial derivative of f with respect to x equals to partial derivative with respect to x of function f, which is the same as saying that, very well, partial derivative of function z with respect to x, or f sub 1. This sub 1 is related to the first variable, or d sub 1 of f, the derivative of function of f with respect to the first variable. In this case, your first variable is x. Next, you can take the partial derivative of f with respect to y, different notations, f sub y, the derivative of f with respect to y. Taking the derivative of f with respect to y, you know that this derivative is just an operator, which is the same as taking the derivative of function z with respect to the second variable y, this 2 representing the second variable, d sub 2 of f, taking the derivative of f with respect to the second variable, and finally d sub y of f, taking the derivative of f with respect to y. All of these are partial derivatives because you have 2 free variables. Okay, one example here for you. Compute the partial derivatives of a function in 2 variables x and y, which is x squared y to the 5th. Since you have 2 free variables, it doesn't make sense to say that take the derivative of the function. You have to mention with respect to which one. Are you taking the derivative with respect to x, or you're taking the derivative with respect to y? You're calculating the rate of change of the function with respect to 2 variables. Very well. Taking the derivative of f with respect to x, we have to consider y, second variable, as a constant. So y is a constant. We fix y and we take the derivative with respect to x. Remember that if you have a power function, x to the n, the derivative is equal to n x to n minus 1. Since y is fixed, or you considered y as a constant, you can just copy down y to the fifth in front of the operator and then take the derivative of x squared. Y to the fifth times 2x, or 2x y to the fifth. The same process when you're taking the derivative with respect to y. Now you consider x to be a constant or fixed. Very well, since x is just a constant, you can write x squared outside the derivative operator. Then take the derivative of y to the fifth, which is 5y to the fourth. The outcome is 5x squared y to the fourth. Very well, let us move on to next example. Now we're interested in actually finding the rate of change of the function at a given point. Suppose function f of x and y is equal to x cubed plus x squared y to the third minus 2y squared. Question says, first of all, find the partial derivative of the function with respect to variable x, then plug in 2 for x and 1 for y. Then it also says, find the partial derivative of function f with respect to variable y, then plug in 2 and 1. So first, we take the partial derivative, then we plug in the value. So first of all, you're taking the derivative with respect to x. You assume y is just a constant. The partial derivative is going to be 3x squared. The derivative of x cubed is 3x squared. Remember that x cubed is just a power function. The derivative of x squared, y to the third. Y to the third, since y is just a constant, you copy down y to the third. And the derivative of x squared is 2 times x. And finally, the last term is just a constant. The derivative is going to be 0. Then you plug in 2 for x and 1 for y. You get 3, 2 squared plus 2 times 1 cubed minus 0, 0 doesn't count, which is equal to 16. The rate of change of function in the direction of x-axis at the point 2 and 1 is going to be 16. The same process when you're taking the partial derivative of f with respect to y. You assume x is just a constant. So the derivative of x cubed is just 0. So this is officially 0 plus. Then x squared, you copy down x squared, then you take the derivative of y cubed, 3y squared. Now you have negative 2y squared, which is minus 4y. Now you plug in 2, you plug in 1, you get 0 plus 2 squared times 3, and y is 1, 1 squared minus 4 times 1, which is 8. Very well. More interesting examples. Here you have a sine function. Your sine function has another function inside it. Here you have a rational function x divided by 1 plus y, which is a rational function. And the question says, very well, calculate the partial derivative of f with respect to x, partial derivative of f with respect to y. You are getting back to Math 1A using the techniques in taking the derivatives of functions. Perfect. So since you have a sine, remember that the derivative of sine u is u prime cosine u. So you have to use chain rule to take the derivative of the quantity inside parentheses multiplied by cosine u. In the first case that you're taking the derivative with respect to x, your y is a constant. Y is fixed. So you're not worried about your denominator. It's like taking the derivative of x divided by 1 plus a. The derivative is equal to 1 over 1 plus a, because y is just a constant. So the derivative of x over 1 plus y with respect to x is 1 over 1 plus y. Then for sine, the derivative of sine is now cosine. And you copy down the quantity which is inside parentheses. Very well. Now take the partial derivative with respect to y. Now you assume x is fixed and you repeat the process. Note that since you are taking the derivative with respect to y, you have to apply quotient rule. Here you have a divided by 1 plus y, and you are taking the derivative with respect to y. X is fixed. X is a constant. So we are taking the derivative with respect to y. You can write down y outside the derivative. So a, the derivative of numerator is 0 times 1 plus y minus the derivative of 1 plus y is 1 times 1 divided by 1 plus y squared. So this derivative is a negative 1 divided by 1 plus y squared. Your a is x, so you have minus x divided by 1 plus y squared. Applying quotient rule. Let me write down quotient rule here for you. U over v prime is u prime v minus u v prime divided by v squared. So the derivative of x over 1 plus y with respect to y is a quotient expression negative x over 1 plus y squared. And the derivative of sine, as we mentioned before, is just cosine. So you'll copy down cosine x over 1 plus 1. And these are the partial derivatives of the function with respect to x, with respect to y. Very well, let's see what's next. Nice. Another function, another trig function sine x squared y to the fifth. And the question says, find the partial derivative of the function with respect to x. It means that your y is constant. Okay, y is constant, and we are taking the derivative of sine of u. The outcome using chain rule is u prime cosine u. So we have to take the derivative of x squared y to the fifth with respect to x. The derivative of x squared y to the fifth with respect to x is equal to 2x y to the fifth. So 2x y to the fifth times the derivative of sine is cosine, and the quantity inside parentheses is x squared y to the fifth. This is the partial derivative of this function with respect to x. Very well. I expect you to ask, how do we find second partial derivatives? So to find second partial derivative of the function, which is denoted by partial derivative of f with respect to x, and you are taking the partial derivative with respect to x again. Remember that here you have partial derivative of f with respect to x, partial derivative of f with respect to y. So you are taking the second derivative of the function with respect to x. You're taking the second derivative of the function with respect to y. Now you are taking the second derivative of the function with respect to x, second derivative of the function with respect to y. First of all, you find first derivative of the function with respect to x, then you take the derivative with respect to x. The notation that you can use is partial derivative squared divided by rounds x squared. The same for the rest of them. First, we take the partial derivative of f with respect to x, then we take the partial derivative of f of x with respect to y. Here you have partial derivative of f with respect to y, then you take the partial derivative of f of y with respect to x. And the last one, we take the partial derivative of f with respect to y, which is the inside function, and we apply the derivative operator with respect to y to the partial derivative of f with respect to y. Let us go over one example to feel more comfortable about these. Perfect. Here you have a function in two variables, x cubed plus x squared y cubed minus 2y squared. So to find second partial derivatives of the function, first we have to take the first partial derivative of the function with respect to x, then with respect to x and y. So the first partial derivative of the function with respect to x, the derivative of x cubed is 3x squared. The derivative of x squared is 2x. And since y is a constant, you copy down y cubed. And since y is a constant, the derivative of the last term with respect to x is 0. Okay? Now we want to take the second partial derivative of the function with respect to x. The derivative of 3x squared is 6x. The derivative of 2x y cubed with respect to x is 2y cubed. Now we want to take the derivative of the function with respect to y. So y is the outside variable. The inside variable is f of x. So you again use f of x. The derivative of 3x squared with respect to y is 0. The derivative of 2x y cubed with respect to y is 2x times 3y squared, which is 6x y squared. Now for the second partial derivative using f of y. Okay, so the outside variable is x. We are taking the derivative of f of y with respect to x. Here you are using this function here. The derivative of 3x squared y squared with respect to x is 6x y squared, and the derivative of 4y with respect to x is 0. So the outcome is just 6x y squared. Now the second partial derivative of the function with respect to y. Again, we're going to use the same function. Partial derivative with respect to y of 3x squared y squared minus 4y. Now your free variable is y. So the outcome is 3x squared times 2y, which is 6x squared y, minus the derivative of 4y with respect to y is 4. Next, partial differential equations. So partial differential equations, you might see it before, you might not taken partial differential equations before. We have a very famous theorem, Laplace equation, which says that, okay, second partial derivative of u with respect to x plus second partial derivative of u with respect to y is 0. If you solve this equation, then the solution set or the family of the solutions are called harmonic functions. Let's take a look at one example, see what's going on. Can we apply this equation and harmonic functions somewhere? Suppose function u is defined as e to the x sine y, and you know that this guy is a solution of your Laplace equation. So if you plug in this function into the equation, the outcome is 0. Okay? To show that this is a solution of this equation, we have to find second partial derivatives of the function. So let us take the derivative of the function with respect to x. then take the derivative of the function with respect to y, then work with second partial derivatives. Perfect. Here you have e to the x sine y. The derivative is equal to e to the x sine y. Remember that. In general, if you have e to the u and you're taking the derivative, it is using chain rule is u prime e to the u. So when you're taking the derivative of e to the x, it is x prime, which is 1, times e to the x, or nothing but e to the x. You are taking the derivative with respect to variable x. It means that your y is a constant. So you copy down sine y, and the derivative of e to the x is just e to the x. Now you can take the second derivative of the function with respect to x again. The same process, e to the x sine y, taking the derivative with respect to x. The derivative of e to the x is e to the x, and you copy down sine y. Now the derivative of the function with respect to y. Very well. E to the x has no y in it, so you can just copy down e to the x. The derivative of sine y with respect to y is cosine y. The first partial derivative of the function with respect to y. Now we take the second partial derivative of the function with respect to y. Again, e to the x has no y in it. You have to copy down e to the x. The derivative of cosine is minus sine. Perfect. So the second partial derivative of the function with respect to x plus the second partial derivative of the function with respect to y is e to the x sine y plus negative e to the x sine y. As you can see, these two terms are opposite of each other, and the outcome is equal to 0. So we just showed that u of x and y e to the x sine y is a solution of this equation. Perfect. Let us move on to equation of tangent plane. Remember that in pre-calculus, in calculus 1a, you learned about a tangent line, y equals mx plus b. So recall, equation of tangent line is y equals to mx plus b, and m is the derivative of the function at given number. Tangent line. So when it comes to functions in two variables, you're interested in finding a tangent plane to your surface. Here, instead of having just a curve, you have a surface. This blue object here is a surface in three-dimensional space. So you're interested in finding a tangent plane, not a tangent line, a tangent plane to this surface. So in general, if you have a function with continuous partial derivatives, then the equation of tangent plane at point x sub 0, y sub 0, z sub 0 is defined this way. Z minus z sub 0. If you plug in x and y here, you can find the z sub 0 is equal to the partial derivative of f with respect to x at the given point times x minus x sub 0 plus partial derivative of f with respect to y at the given point times y minus y sub 0. That's the equation. And this equation gives you this tangent plane, tangent to the surface. So we have to calculate partial derivatives as rate of change with respect to x and rate of change with respect to y. Here you have two variables. We need two rate of changes. We have two free variables, x and y. So we need two rates of change. Perfect. Let's cover one example to see what's going on here. How do we apply this equation? Perfect. Here you have a function in two free variables, x and y, and the question says find equation of tangent plane at the given point 1, 1, 3. Very well. To apply the formula, let's take a look at the formula again. Z minus z sub 0 is equal to f of x, x minus x sub 0 plus f of y, y minus y sub 0. So first of all, you need to find partial derivatives. So z minus z sub 0 is equal to f of x, x minus x sub 0 plus f of y, y minus y sub 0. Luckily for us, z sub 0 is given. It is 3, z sub 0, the last coordinate. So 1 is x sub 0, y sub 0 is 1, and z sub 0 is 3. X sub 0 is 1, y sub 0 is 1. Z is a variable, you copy down your variable, equals to f of x is missing, parentheses, x is a variable, minus is just subtraction, plus f of y is missing, y is a variable, you copy down your variable, and minus is just a subtraction. So let us take the derivative of the function with respect to x. First of all, the first term has x in it, so the derivative is 4x. The second term has only y in it, so the outcome, the derivative is 0. Now you have to evaluate the partial derivative with respect to x at x1, y1, which is 4. So my partial derivative of the function with respect to x is 4. Now we have to take the partial derivative of the function with respect to y. It means that your x is now a constant. So 2x squared is just a constant. The derivative is 0. And the derivative of y squared is 2y. Then you have to evaluate the function when x is 1, y is 1. You don't have any x in it. So 2 times 1 is 2. Partial derivative of f with respect to y is nothing but 2. So you're done with calculus part. The rest is algebra. Z minus 3 is equal to 4x minus 4 plus 2y minus 2. Let us simplify this, write it in nicer format. Z minus 3 is equal to 4x plus 2y minus 6. So z is equal to 4x plus 2y minus 3. Equation of tangent plane to the surface. Very well. Let us move on to the next page. Differentiability. So we say that a function on a domain like D is differentiable if partial derivatives of the function exist and they are both continuous. Function f is differentiable on a domain which is usually an open disk if partial derivatives exist and both of them are continuous. If you have a differentiable function like z equals to f of x and y, we can define differentials dx, dy. Guys, these are not partial derivatives. These are differentials of the function. They have directions. To be independent variables, it means that you can define the differential of the function as a total differential dz equals to partial derivative of f with respect to x times the direction x plus partial derivative of f with respect to y times the direction dy. So if somebody asks you to define the total differential of a function, you have to follow this formula. dz equals to partial derivative of f with respect to x times the direction of x plus partial derivative of f with respect to y times the direction of y. For example, suppose you have a function z equals to f of x and y, x squared plus 3xy minus y squared. Question says find the total derivative, the total differential of this function. Very well, we have to take the partial derivative of f with respect to x, so f of x and f of y. When you're taking the partial derivative with respect to x, it means that your y is just a constant, so you get 2x plus 3y minus 0. Now you take the derivative of function f with respect to y. The first term has no y in it, so it is 0 plus 3x minus 2y. And you have to copy down dx and dy because these are showing the direction of the function. Very well. What else do we have? Okay, another example for you. Suppose a function in two variables is given 5x plus 4y squared, and you know that this function is differentiable. It says find the equation of the tangent plane at the given point 2 and 1. Perfect. So first of all, we have a nice formula. We know that the tangent plane follows z minus z sub 0. It's equal to f of x, partial derivative with respect to x, x minus x sub 0 plus partial derivative of f with respect to y times y minus y sub 0. Okay, let's see what information are given. Z is a variable, so it's just a variable. Z sub 0 is not given. You only have the first two values, x and y are given. Equals to, do we have f of x? Nope. X is a variable, x sub 0 is 2, plus, what about the second partial derivative here? Nope, we don't have f of y. Y minus y sub 0 is 1. Okay, how do we find z sub 0? If you plug in 2 for x, 1 for y, you can find your z value. F of 2 and 1 is equal to 14, and 14 is z sub 0. So z minus 14 is equal to f of x, x minus 2, plus f of y, y minus 1. We have to take the derivative of the function with respect to x. The derivative of 5x with respect to x is 5. And since 4y squared has no x in it, the derivative is 0. Very well. We found our partial derivative with respect to x, 5. So z minus 14 is equal to 5, x minus 2 plus. Now let us take the derivative of the function with respect to y. The derivative of 5x is 0. The derivative of 4y squared is 8y. And you're calculating this guy when x is 2, y is 1. So 1 times 8 is 8. Now let us write this guy in nicer format. Z minus 14 is equal to 5x minus 10 plus 8y minus 8. So z minus 14 is equal to 5x plus 8y minus 18. So your z is equal to negative 4 plus 5x plus 8y. This is also called the linearization of function at point 2 and 1. Exact same thing as your tangent plane. Okay, we can look at